So we'll wait for 1 minute and then we'll begin. So are there any questions so far? If there are any doubts, then we can take it up before starting. All right, if there are no questions from previous lectures, let's begin. So, since basic objects in the universe that are directly visible to our naked eyes because of their own energy production processes are stars. And as we have been repeatedly mentioning, stars are bright because of the thermonuclear fusion that is happening at the center of these objects. And the reason why the thermonuclear reactions take place at the centers of the stars is because of the intense pressure and temperature at the core. In fact, the first question in the assignment set 1 was about estimating approximately the pressure in the core of a star. And the idea was that if the core has a radius 1/100th the total radius of the star, then the way to estimate was take the total weight of the matter around the core. Weight by weight, I mean mass times average gravitational acceleration, which will give us the weight of the matter directed toward the center, and balance it by the force exerted by the pressure due to the core. And that is the method by which you all are supposed to estimate the central pressure. And once the pressure, uh, which is due to Pascal's law, is in all directions, but the force of the core would only be outwards on the envelope surrounding the core, by using the fact that the core force equals the weight of the surrounding matter, you get the condition of the hydrostatic equilibrium. And that is the reason why stars are in quasi hydrostatic equilibrium, arising out of the intense pressure generated by the thermonuclear processes going on in the. But then you might wonder that stars are very far away from us. After all, sun, the closest star to the earth itself, is more than 10 raised to power 13 centimeter away from us. And therefore, how do we measure various aspects of the stellar surface, stellar size, and so on? We cannot go to the star and carry out measurement in situ regarding the surface temperature or the size of the star. So, what is the way we adopt in order to estimate the temperature, the size, and other physical parameters of a star? And here lies the greatest use of fundamental physics. Since laws of physics are universal in the sense that if the laws of physics hold good on Earth, it must hold good everywhere. And hence, we can apply the laws of physics even to objects that are very far away from us. And since it is the electromagnetic radiation which primarily bring information about stars, we therefore make use of many aspects of electromagnetic radiation to study the physical nature of stars. We also know from the spectrum of various stars that photosphere of a star is like a black body. If one studies the spectrum of the closest star, namely the sun, that the continuum spectrum indeed has a feature like this. That is, if you plot the brightness of the photosphere of sun as a function of the wavelength, you will find that the brightness increases as you go to longer wavelength. It attains a maximum somewhere between 550 and 575 nanometer, and then again it starts falling. What I'm talking about is the continuum radiation from the sun. There'll be, of course, absorption features, emission features, because of various elements that are present either near the photosphere or above the photosphere. But if one removes the discrete features that arise because of the quantum nature of atoms and study just the continuum radiation. The continuum radiation, by the very word, means that the brightness is a continuous function of the wavelength. Then one indeed sees a typical black body radiation form. And there are stars which are cooler. For example, from the continuum spectrum, you can estimate temperature of sun, and sun's photosphere is about having a temperature of about 6,000 degree Kelvin. While if you take a red giant star, then the continuum emission would be something like this, and therefore the temperature is lower compared to the sun, and it is around 700 nanometer. While a very hot star like O star or B star, they are extremely hot, and their spectrum would trace out a black body spectrum corresponding to a higher temperature. So OB stars are very hot and they can have temperatures close to 18,000 degree Kelvin. This is the so-called black body brightness temperature. If you integrate out over the wavelength and ask what is the flux of black body radiation, flux meaning amount of energy radiated by a black body at temperature T per unit area per unit time, then you get the expression that the integrated flux is sigma T raised to power 4, where sigma is called the Stefan-Boltzmann constant. And you see the standard result that we use in laboratory physics in various thermodynamics experiment. And we see that the dependence on temperature is fourth power of the temperature. All right. So the energy radiated by a black body per unit area per unit time is given by this Stefan-Boltzmann law, which is sigma multiplied by fourth power of the temperature of the black body. And Stefan-Boltzmann constant, as you all know, is about 5.67 into 10 to the power 8 watts per meter square per fourth power of Kelvin. Okay. So, by measuring the continuum spectrum of a star, we can estimate the surface temperature. But note that prior to very high resolution telescopes like Hubble Space Telescope, and also because of the atmospheric seeing condition, the uh, upper atmosphere is highly turbulent, because of which we all know uh, very small apparent sized object like stars, they appear to twinkle, while objects whose apparent size is bigger, they don't twinkle like planets. While stars, because they are, although the intrinsic size is much bigger, but since the distance at which most of the stars are enormously large, their apparent size, that means what is apparent size? Actual size divided by the distance, so-called angular size. Since it's very tiny for stars other than sun, they appear point-like, and because of the turbulence, the refractive index changes, and hence the position keeps fluctuating, and that is the reason why stars appear to be twinkling. Now, a natural question would be, how do you then estimate the radius of a star which appears in ideal atmospheric condition to most Earth-based telescope? It just appears like a dot. How would one measure the radius of such a such an object? Now there are steps involved in estimating the radius. The first step is find out the luminosity of the star. Of course, there one assumption is involved assumption is radiation is being emitted radially and isotropically outwards, which is a good assumption. For example, sun, because of it being approximately a spherically symmetric object, the radiation from the photosphere of the sun is more or less isotropic. And this is a good assumption for most stars. If we assume that stars radiate in an isotropic fashion, then we know that if the photosphere is emitting at the rate L, L being the luminosity, so if L amount of energy per unit time is being radiated, and if it is being radiated isotropically, and we are sitting at a distance r, then as it reaches us, this L amount of radiation per unit time, it will, by the time it reaches us at a distance of r, this energy will be distributed over a sphere of radius r, and therefore the amount of radiation that our detector will detect per unit area will be L divided by 4 pi r square. So here the assumption is that star that a star is emitting in an isotropic fashion, and Euclidean geometry, which tells us that surface area of a sphere of radius r is 4 pi r square. These two facts have been used. In other words, by measuring the flux, which is the amount of energy that our telescope is detecting per unit area per unit time, by measuring the flux and by knowing the distance of the star from us, we can find out what is the luminosity of the star. So, luminosity, which is the luminosity of the photosphere, and that is the amount of energy the photosphere as a whole is emitting per unit time, can be figured out by measuring the flux and the distance of the star. Then I'd already pointed out to you that photosphere of most stars, if you look at the continuum radiation, it emits like a black body. Thereby, the amount of radiation that an unit area on the photosphere will be emitting per unit time will be given by the Stefan-Boltzmann law. So, a unit area of the photosphere will be emitting radiation sigma t raised to power 4 per unit time. Okay? And temperature, how did we estimate the temperature of the photosphere? By measuring the spectrum. If the continuum spectrum, continuum spectrum is measured using a dispersion technique like either a very good quality prism or diffraction grating and what have you, you can measure the brightness as a function of wavelength of the photosphere. Therefore, one would be able to find out the temperature of the photosphere using the photometry and telescope. So temperature is estimated using photometry. That means a telescope which is having with it either a very good quality diffraction grating or a prism, so that it can measure the intensity of radiation from the photosphere as a function of the wavelength. So temperature can be measured observationally of a star photosphere. Flux is measured directly by looking at the total radiation the detector is collecting, detector the telescope is collecting per unit area, per unit time. So flux is measured, temperature is measured. Distance has also been estimated by various means. If there is a star within few parsecs, you can use the parallax method that I mentioned to you in my first or second lecture. So distance is measured, temperature is measured, flux is measured. Hence, I can find luminosity from the relation that the flux is luminosity divided by 4 pi times distance square. So that luminosity is simply 4 pi distance square multiplied by the flux. Okay? So luminosity becomes flux times 4 pi distance square. But we also know that the flux, the luminosity is also, so remember, this relation will directly give me the luminosity in terms of measured flux and measured distance. But we also know that if the photosphere is acting like a black body, that means what? Per unit photosphere, per unit area of the photosphere, amount of radiation per unit time is sigma multiplied by T raised to power 4. The photosphere total area is 4 pi times size square. That means if the star has a radius r0, then the photosphere surface area is 4 pi r0 square. Okay. So 4 pi r0 square, where r0 is the radius of the star, 4 pi r0 square is the surface area of the photosphere. I'm assuming that the star is of spherical shape. Okay? If a star is rotating, a little bit of bulge will be there, but you can show that even for a very rapidly compact star like the neutron star, the bulge is not very appreciable. Hence, the assumption that a star is approximately a spherical body is a good assumption. Okay? So therefore, 4 pi times r0 square, where r0 is the radius of the star, 4 pi r0 square is a good estimate of the surface area of the star. And now if I use the Stefan-Boltzmann law, then the luminosity of the star has to be sigma T raised to power 4. So luminosity becomes sigma T raised to power 4 multiplied by the surface area of the star, which is this relation. So 4 pi r0 square into sigma T raised to power 4 is the luminosity. But luminosity is also equal to flux times 4 pi distance square, and hence the only unknown is the size or r0, and therefore we can find out the radius of the star using the information that luminosity is flux multiplied by 4 pi distance square, and luminosity is also sigma t raised to power 4 multiplied by 4 pi r0 square. Using this two relation, we can estimate the size of the star. Okay. I'll come back to it in a moment. So there's a summary of how we estimate the size of a star is we know the luminosity from the flux and distance, but we also know from thermodynamics if the surface of the photosphere emits like a black body, then luminosity must also be equal to sigma t raised to power 4 times 4 pi r square, which is the surface of the photosphere. And therefore, we know the luminosity as 4 pi r square into sigma t raised to power 4. But luminosity is also equal to flux into 4 pi d square is the distance of the star. Using this, we can now figure out what the radius of the star is. Okay. Right. So I will, in my second assignment set, I will give you some problems to use this idea of making the measured quantities like flux, distance, temperature, and infer quantities that are not directly measurable, like whether it is the luminosity or whether it is the size of the object. And as discussed earlier, mass of a star can be obtained either using dynamical method means if the star is having a binary companion, that means if you have a binary system, then looking at the rotational motion of the star and the binary component and using the gravitational rule, you can find out the mass. Just like the exercise I have given you to find out the mass of Earth using Moon's rotation around Earth, or finding out the mass of the Sun using Earth's rotation around Sun. On the other hand, stars which are isolated stars, that is, they are not binary system, to estimate the mass, we have to use the full stellar evolution theory. We have to first find out whether the star is a main sequence star. Then, if it's a main sequence star, then we use the temperature of the photosphere and size of the photosphere, etc., and use the theoretical modeling of main sequence stars to arrive at the mass of a star. So that such estimation of mass is theory dependent, but uh, by now most astronomers and astrophysicists have stupendous confidence in the theoretical modeling of stars from the days of Chandrasekhar onwards, and particularly use of Saha's ionization equation. Many things can be determined very well and stellar evolution theory is a well understood subject. Now, you might wonder that suppose we have a celestial body for which we can estimate the luminosity by some other means. Okay, that means if I have an independent way of measuring the luminosity, then by measuring the flux, we can estimate the distance of the star, distance of this celestial body. Just like if you know that a distant street light has a specified wattage like 1000 watt. So supposing you know that very far away a street lamp that has been installed, the the wattage of the street light is 1000 watt. That means it is emitting energy at the rate of 1000 joules per second. Then by measuring the flux of radiation that is reaching you, you can find out what is the distance of the street lamp from you. Of course, here I am assuming that the seeing of the day is good. That means there is no that winter, because of foggy condition in winter, uh, the seeing gets influenced by it. Sometimes it can become so foggy that you can't see anything beyond 3 to 4 meters away from you. I'm assuming that your the day is such, day or evening is such that there is no absorption or scattering of radiation from the street lamp to where you're standing with your photo detector. Okay. Similarly, if you have a celestial source which can act like a standard candle, that means the luminosity can be measured independently, then by making measurement of the amount of energy received per unit area per unit time at the telescope, one can immediately find out what is the distance r of the source from us. So always such standard candles are sought after in astronomy. But first of all, are there such standard candle? The answer is yes. And first such standard candle was actually discovered by Dr. By Lady Henrietta Swan Leavitt. When she discovered this standard candle, namely the Cepheid variables, the work was very important, and people like Hubble, they used it to settle one big debate as to whether the nebulae like Andromeda, etc., which we are seeing, are within our galaxy or outside our galaxy. So, using the standard candle nature of Cepheid variable, Hubble established that Andromeda is a separate galaxy. But all these epochal discoveries later were made based on the work which Lady Henrietta Swan Leavitt uh, did. And during her time, she was not given due uh, honor for her such a fundamental work in the field of astronomy. Now, before I discuss what Henrietta Swan Leavitt accomplished, I must tell you about a particular quantity that astronomers use, and that is the notion of magnitude. Okay, so let me go to the slide where I talk about this particular concept. Okay, now it turns out that our eyes, when they look at objects like stars, the whether some star is brighter by twice the amount or thrice the amount, it turns out that our human eyes, the response goes in a logarithmic fashion. So, historically, when an astronomer said that this is a star of magnitude 1, this is a star of magnitude 2, what that time the astronomer, ancient astronomer, did not realize is that when you say magnitude 2, it doesn't mean that its brightness is half of magnitude 1 star. Okay? Rather, magnitude goes in a logarithmic fashion. Let us become more specific in describing this idea of magnitude in astronomy. So please pay attention. Supposing I have two stars and I'm using my telescope to measure the flux, star 1 and star 2. For star 1, if my telescope measures the flux to be F1, and for star 2, the telescope measures the flux to be F2, then it turns out that the old classification of magnitude is that the magnitude of star 1, if I call it M1, and magnitude of the star 2, if I call it M2, then M1 minus M2 is equal to minus 2.5 log base 10 of the ratio of F1 to F2. So I hope I have made myself very clear. So magnitude was a system that was used by old astronomers based on naked eye observation. But today we can relate it to proper measurement, and what I have just mentioned, let me repeat it again. If there are two stars, 1 and 2, and your telescope measures flux from star 1 to be F1 and flux from star 2 to be F2, then magnitude M1 minus magnitude M2 is minus 2.5 log 10 of F1 divided by F2. So what does it mean? If F1 is bigger than F2, that means more amount of radiation from the star per unit time per unit area is received from star 1 compared to star 2, then M1 minus M2 will be actually smaller because of this minus 2.5 factor. Okay. In other words, you can take the inverse of this result. If you take the inverse of this result, then you get F2 divided by F1 is 100 to the power M1 minus M2 divided by 5. So if F2 is smaller than F1, then M2 is larger than M1. Some example, by the way, this M1, small m2, they are called apparent magnitude of star 1 and apparent magnitude of star 2 respectively. Remember, these are very simple things. They are just conventions which astronomers use to link modern measurement with the classification of older astronomers who used naked eye to describe the brightness from a star. They are very simple stuff. I'm sure a little bit of familiarity would convince you about the nature of apparent magnitude M1 and apparent magnitude M2. Some examples of apparent magnitude. As you can see, fainter an object that appears to you, the magnitude, apparent magnitude is very large. So if I take the star Vega to have magnitude 0, just a convention. So due to some reason, old astronomers thought that Vega is a very bright star. So if you take Vega to be having apparent magnitude 0, in fact, the star Sirius, the brightest star that we see from northern hemisphere, the brightest star from the northern hemisphere is Sirius, the so-called dog star. As you know, when we described the Orion constellation, I told you that the Sirius constellation is towards just a little below the right leg of the Orion constellation. And the brightest star of the Sirius constellation is the Sirius A star. And you can see Sirius star's magnitude is negative. That means it's very bright. Venus appears even brighter. Its magnitude is -5. Moon is even brighter because Moon is closer, although neither Moon nor Venus, they produce their own energy. They only reflect the amount of radiation they receive from the sun. But because they are close by, therefore their apparent magnitude is more negative. That is, they appear much brighter than stars. Quasar, we know quasars are very luminous object, but because they are very far away, their apparent magnitude is very large and positive. Okay. So as you go to fainter and fainter objects, the apparent magnitude keeps on increasing. While the objects that appear to us very bright, the apparent magnitude is more negative. Sun, in fact, is somewhere here. Its magnitude is less than -25. That means it's very bright. Okay. So again, I will give you one or two problems in the assignment set 2 so that you get some familiarity with the magnitude scheme. And those who later on would like to become optical astronomers, they necessarily use the magnitude scheme due to historical reasons. On the other hand, radio astronomers would talk about flux density or brightness temperature and so on. But for optical astronomers, magnitude classification is very, very important. Now let us, okay, but before I go back to Henrietta Swan Leavitt's work, let me also mention another thing. So far, I mentioned about apparent magnitude, but you might wonder, isn't there some quantity which tells me about the actual luminosity of the star or of the object? That is, actual amount of radiation per unit time that the object is throwing out in the space? Yes, the answer is to the question is yes, and that is the absolute magnitude. Apparent magnitude is normally denoted with small m, while for the same object, the absolute magnitude is written with capital M. And the from this definition, note that if I have an object whose apparent magnitude is small m, then if it is absolute magnitude is capital M, then we have a relation which has been defined in the following way, that small m minus capital M is 5 times log base 10 of distance of that object in units of 10 parsec. And from that you subtract 5. So what you do is, if you know the bright object's distance from us, measure that distance in units of 10 parsec. That means supposing the distance of that bright object is 1000 parsec, then d will be 1000 parsec divided by 10 parsec, that means 100, and you will put 100 in this place. Evaluate 5 log 10 of 100 minus 5. That will be the apparent magnitude minus the absolute magnitude. In other words, what this equation is telling us is the absolute magnitude of a bright object is nothing but the apparent magnitude that bright object will have if it is put at a distance of d in units of 10 parsec. Okay, is that clear? So, because if that bright object is brought to a distance of 10 parsec, then log 10 of, okay, wait a minute, this, well, if you take this equation, I have made a mistake here. It's not 10 parsec, it is unit of 1 parsec. Okay, here I have made a mistake. This is not 10 parsec, please correct it. This d is distance in units of 1 parsec. Please make that correction. There's a typographical error here. The distance d is in unit of 1 parsec. So again, let me repeat, because there's a typographical error. Let me repeat. The apparent magnitude small m minus absolute magnitude capital M of an object is 5 times log base 10 of distance in unit of 1 parsec minus 5. And therefore, the absolute magnitude is nothing but apparent magnitude provided that object is brought to a distance of 10 parsec. As you can see, if you bring an object to a distance of 10 parsec, d becomes 10, log base 10 of 10 is 1, so 5 minus 5 becomes 0, and then apparent magnitude becomes the absolute magnitude. Okay. Right, so I hope I made it clear as to what an apparent magnitude is and what an absolute magnitude of an object is. And as an example, you can see that take the Sirius A star. Here is Sirius A star. Sirius A star, as I told you, that is the brightest star that can be seen from the all countries which are in the northern hemisphere of our globe. The brightest star which can be viewed from the southern hemisphere of the globe is actually Canopus. The Sanskrit name of Canopus is Agastya. Now, Agastya, the story goes like this, that uh, the Canopus star from Delhi can only be seen at the horizon. And because the horizon you never see properly, you can never see, it's very difficult to see Agastya star from Delhi. But if you go to Pune, a little bit southwards, you can see Agastya star. If you go to Chennai, Agastya can be seen prominently much above the horizon. And according to the legend, we all know that Agastya was the first Vedic rishi who crossed the Vindhya mountains to go southwards. And the reason why this southern star has been named Agastya is probably the Vedic seer Agastya. He was the first Vedic person who Indo-Aryan who went from north to south and spotted a very bright star, and probably that is the reason that bright star of south has been named after Agastya. Yeah, but let me come back to the question of apparent magnitude. Since Sirius A is the brightest star as seen with our naked eye, and you will find that very faint star is there, which is HD 49980. Here you can see the faint star, which is circled by a red circle. It appears very faint. In fact, if you take a photograph of using telescope, you will find the Sirius A. Of course, this is not the size of the star. It is because of the point spread function of the telescope. It leaks out. The Sirius star appears very bright, and HT 49980 appears very faint. But in reality, if you do all this calculation, because uh, HD 49980 is much further away, and if you do the calculation, then you will find that indeed the absolute magnitude of HD 4980 is much more negative than the absolute magnitude of Sirius A. Sirius A appears brighter because it is closer to us. Now, if you go to this reference from which these images have been taken, if you go to the reference, there are a lot of nice, interesting, simple numericals you can do to become more conversant with the idea of apparent magnitude and absolute magnitude. But before I leave the slide, again, I draw your attention to the typographical error. This should be 1 parsec, not 10 parsec. So your D is measured in unit of 1 parsec. All right. So I hope I have given you a flavor of the notions of apparent magnitude and absolute magnitude. Now let me go back to what Henrietta Swan Leavitt, what she discovered. There's a class of stars called Cepheid variables. By the very name, you can imagine that these stars, their brightness vary with time. Okay? And what Henrietta Swan Leavitt observed was that if you look at the maximum absolute magnitude of the Cepheid variables, then there is a correlation with the variability time scale. Okay, I'll show you another picture. Here it is. So if you plot the absolute uh, magnitude, then the magnitude changes with time. And why does it change with time? The reason is that we have already established bigger the star is, they tend to be more luminous. Of course, the temperature is also there coming in. But it so turns out that for Cepheid variables, when they become larger, the luminosity is large and therefore their brightness is bigger. All right. Of course, by brightness bigger, the magnitude becomes more negative. Here in the y-axis, what is being plotted is the brightness. So the brightness of a Cepheid variable, they are more or less periodic. And what was inferred by Henrietta Swan Leavitt was that there is a correlation between the brightness and the period over which the Cepheid variables vary. Okay. So here is the actual data what she obtained. So if you actually plot, right, if you actually plot the apparent magnitude of these stars, then the apparent magnitude and the period of the star, there is a correlation. So here is the maximum brightness of the star, and here is the minimum brightness of the star. So from this, one can therefore independently measure the luminosity. By looking at the variability time scale, one can find out what is the actual luminosity, and therefore by measuring the flux, one can find out the distance of the star. So Cepheid variable was indeed very important for astronomy because it gave an a powerful method of finding out distance of different celestial object, and it was of great use for Edwin Hubble, an American astronomer, who used it in conjunction with another quantity that I will talk in my next lecture to obtain one of the most important uh, laws that talked about the entire universe as a whole. Okay. Right. Now, today I will end my lecture. I will spend more time answering questions after this, but today I will end my lecture with this very interesting puzzle. So imagine we have a star like sun, and we know that the photosphere of the sun is very hot at a temperature of 6000 degree Kelvin. And we have already discussed the fact that after billion years, when the core gets depleted of hydrogen, when uh, the core has heavier element, then no more nuclear fusion takes place in the core, but the envelope surrounding it, it still has hydrogen. When the core shrinks, the envelope also shrinks and becomes hotter, and the envelope starts burning hydrogen, namely 4 proton become 1 helium nucleus, and the envelope therefore becomes heated up, and that makes the star expand, and it expands into a red giant. And this picture has been taken So credit goes to Paul G. Beck um, from KU Leuven, Belgium. So red giant, of course, because of the expansion, the radius becomes very large, but temperature of the surface is smaller, and the temperature can become as low as 4000 degree Kelvin. Now you have a sun-like star, let's say. The temperature of the star photosphere is 6000 degree Kelvin. And take a red giant, the temperature of the photosphere is, let's say, 4000 degree Kelvin. Now do the following. You connect it by some thermal conductor. So put a thermal conductor like a piece of copper wire connecting a sun-like star and a red giant star. We all know from our school level physics and from our also experience that heat flows from hotter object to cooler object. Okay? So if I connect the photosphere of our sun to the surface of a red giant star, which is cooler, heat will flow from sun to the red giant. So energy of the sun will get depleted while energy of the red giant will increase. But if sun loses energy, what will happen? If you take a gravitating object and take away its energy, it shrink. The sun will contract. But because I'm taking away extra energy, just like if a satellite is going around Earth and it has certain orbital radius, if due to friction the satellite loses energy, the satellite actually starts spiraling down, and as it starts spiraling down, its velocity actually increases. It loses energy, but it comes down with higher velocity. So similarly, if I connect sun surface by to the surface of a red giant by a thermal conductor, sun will lose energy, and because it loses energy, it will contract, while red giant will gain energy. Because it gains energy, it will expand, and because sun will contract, its temperature will actually go up. Just like the satellite gaining more speed, contracting will make the random velocity of the atoms in the sun to go faster. That means the temperature will go up. While red giant expanding will make it cooler. So surface of the red giant becomes cooler, sun becomes hotter, but then more energy will go from sun to red giant. So it's a runaway process. As the sun loses heat to the red giant, sun shrinks, becomes hotter and hotter, red giant expand, become cooler and cooler, and the whole process goes on. So it's a runaway process. Sun will become hotter and hotter, red giant will become cooler and cooler. It's a paradoxical situation as it will continue to go ad infinitum. And what is the reason for this? Now, I will leave it to you to think about the reason. In the next class, I will discuss as to why this is happening. But at the moment, I leave it to you to think about this paradoxical situation that comes about when I connect the photosphere of a sun like star with the surface of a red giant like star. So, my lecture will stop here, but I will spend more time discussing with you. Are there any questions? Yeah, so there's a question from Ankit. It is, why brightness not going like, okay, I think Ankit is asking about the CFID variable. All right. Now, CFID variable, uh, it requires more theoretical understanding as to why the brightness varies in this. So this happens for variable stars like CFID. Normal stars like Sun, they don't show this variability. The CFID variability is due to the instability brought about by certain convection that is happening in the region just below the surface of the star. So there is an instability because of which a Cepheid-like star is not fully in hydrostatic equilibrium. Okay, so suddenly it becomes hot, and from small side it expands. When it expands, it becomes cooler, and again it contracts, and so on. So dynamics of Cepheid variable is somewhat complicated. So to answer Ankit, this variability is shown by stars like Cepheid and RR Lyrae, etc. The sun does not vary. Okay, the variability requires a full detailed theory involving instabilities. We will not study the theory behind variable stars in this course. Are there any more questions? So again, uh, let me draw your attention. So please go to this reference. These are all available online. Please go to the reference and look at small problems that has been given in this reference and do it so that you can get a good idea of what one means by apparent magnitude, what one means by absolute magnitude. Remember, this has to be corrected. The distance d is in units of 1 parsec. Okay? Yeah, I can understand that why there are less questions, because already, you know, 3 hours of lectures in a day, it saturates one's mind. And that is the reason why I was thinking that perhaps uh, we should postpone the afternoon lectures to some other day, so that you know there is no saturation. Yeah, there's another question by Nancy Chanu. What is the unit of magnitude, or m? How did we take log even though it has a unit? It's a good question. Yeah, but the magnitude doesn't have a unit. But it's a good question. Let me go back. Yeah. So as you can see, magnitude is dimensionless. Why? Because look at the ratio. F1, flux from star 1, has the dimension of physical dimension of energy per unit area per unit time. So does F2. F2 has also physical dimension energy per unit area per unit time. So F1 divided by F2 is dimensionless. So therefore, log 10 of a dimensionless quantity is well defined, and that is the reason why M1 and M2 are dimensionless. And similarly, the absolute magnitude is also dimensionless, because remember, from this equation, it becomes clear that if you have an object in sky with apparent magnitude m and distance d, its absolute magnitude is the apparent magnitude it would have if the object is brought to a distance of 10 parsec. Then you can see m minus capital M will become 0. So both apparent magnitude as well as absolute magnitude, they are dimensionless. Is that clear, Nancy Chanu? Oh, no, no. Rishika, uh, the example of a sun being connected to a red giant star was a thought experiment. There are no stars close to sun. The nearest star, as you know, is Alpha Proxima, which is at a distance of 4.3, about 4.3 light years from our sun, quite far away. I was just talking about a thought experiment in which, if you connect a hot star with a cold star, then you get a paradoxical situation, because heat will flow from the hotter star to the colder star. But because of this, the hotter star will become hotter and hotter, while the colder star become colder and colder. So it was a paradoxical situation. It's not that our sun is interacting with any red giant, because the closest star to the sun is a star called Alpha Proxima, and which is about 4.3 light years away from sun. Yeah, so good question, very good question, Devender. So what Devender is asking is this: in the thought experiment I described, where you have an apparent paradox, I said that as the hotter object is losing energy to the colder object, it is shrinking. And if it is shrinking, it becomes hotter and hotter. So, because, and if it is becoming hotter and hotter, it means that the atoms are moving randomly with greater kinetic energy. So Devendra is asking, if its kinetic energy is increasing, then it can escape from the star. It's a very good question. The answer is no, it will not escape, because remember, it is shrinking. If the size of the hotter and hotter star is becoming smaller, then escape velocity also is increasing. Remember the expression of the escape velocity? Escape velocity is square root of 2gm by r, where m is the mass of the star and r is the radius of the star. So if it shrinks, the random kinetic energy will increase, but escape velocity will also increase as square root of 2gm by r. In fact, you can show that the kinetic energy also increases as square root of r. We'll talk about it in the next lecture, because this comes about from something called virial theorem. We will, in this course, not prove virial theorem. I will only give the statement of the virial theorem. Virial theorem, whenever I teach classical mechanics, virial theorem is derived in the classical mechanics course, and therefore in this course I will not derive or prove the virial theorem, but we will make use of virial theorem because it's a very important theorem as far as astrophysics is concerned. So I hope I have answered your question, Devinder. The kinetic energy will increase, but the rate at which random speed increases is also same as the rate at which escape velocity increases. The second question by Devinder is the internal interaction be enough to keep the particles in the bound state? Well, the particles are in bound state not because of internal interaction. The particles are in bound state because of the self gravity of the star. And gravity being a long range force and being universal, gravity is always acting. And therefore, the as long as the escape velocity criteria is satisfied, the all the atoms will continue to be in bound state. So what I mean to say is that as the star shrinks, the escape velocity also increases. So as long as the average speed of the atoms are less than the escape velocity, they will remain bound to the star. But I will discuss virial theorem and show why when an object shrinks, it continues to remain in a bound system. That follows from the virial theorem. By now, you must have got an idea about the Introductory Astronomy course. Our numerical problems will be very simple. We will not use any differential equation. We will not use any integral or integration, but simple algebra and arithmetic will be used to solve the numerical problems. All right. In other words, our mathematics that we will use in this course will be at the level of Frank Schu's book. In fact, those who are going through Frank Schu's book, The Physical Universe, must have already realized that the numerical problems scattered all over the book, they are very simple and don't require knowledge of either calculus or integration. Simple algebraic manipulation results in solution to the problems. So I advise everyone to solve the relevant numerical problems of Frank Schu so that you get a basic idea about the physical processes that goes on in celestial objects. There are many fascinating things. So I'm not continuing my lecture, but I'm just talking about the fascinating topics that we will talk about, like uh, late evolution of a star, supernova explosion, then things like pulsars, which are nothing but neutron star endowed with very strong magnetic fields, and because of which you get pulses periodically emerging from neutron star. So there are a lot of interesting astrophysical objects that we will discuss in this course, but we will use a very simple mathematics and simple physics to describe all these results. Uh, Can I request students who are from other disciplines, not from uh, the Department of Physics and Astrophysics, can you please give me feedback as to whether the level at which I'm pitching the course is all right with you? Are there students at the moment logged in to this online lecture who are uh, not from the Department of Physics and Astrophysics? Because the feedback is important to me. I want to know, as this is an open elective, and open electives are supposed to be uh, taken by students from outside the Department of Physics and Astrophysics. Therefore, I would like to know um, whether the the level at which this course is being pitched is all right with you guys. Okay, Shruti, no problems. Since this lecture anyway is recorded, please view the lecture in the YouTube. But I would like to have feedback from you as to the level of physics and mathematics that I'm using in the course, whether it is all right. So far, you're saying is all right, but I would like to, uh, uh, after one or two lectures more, I would like to know how what the level is like, particularly from students like Shruti, Ankita Shelley, and others who have credited this open elective. Thanks, Shruti. Yeah. I don't know whether Ankita Shelley is has joined us. I would also like to have her feedback. As I said, that the course will be pitched at the level of Frank Schu's book, The Physical Universe, and I have a feeling that that should be all right. It should be fine for students who are outside um, of Department of Physics and Astrophysics. Okay, if there are no more questions, I think I will close the session. But again, I request you to all get together and find out whether there is another slot other than Saturday afternoon where we can have the 2 hours of lecture, because 4 hours in a single day, it probably, it's not very effective learning process for students, because brain after all has a capacity to absorb things. So please discuss among yourself and find out whether we can schedule the second sessions 2 hours on some other day. Okay, so we will close the session now. Uh, goodbye, everyone. Take care.